The story of quantum mechanics as explained in the following references. Chemistry by Chang, 10th edition. A PDF material entitled The Quantum Mechanical Model of the Atom. Let us begin the story with this picture. This is dubbed as the most intelligent picture. This was taken during the Solvay Conference in 1927. It was a gathering of all the great thinkers of physics in the century. The early part of the 20th century brought changes that revolutionized how we think about physical reality, especially in the atomic realm. The most famous conference was the October 1927 Fifth Solvay International Conference on Electrons and Photons, where the world's most notable physicists met to discuss the newly formulated quantum theory. 17 of the 29 attendees became Nobel Prize winners. The Solvay Conference was considered a turning point in the world of physics and chemistry. The quantum mechanical theory was developed by unusually gifted men of science like Max Planck, Albert Einstein, Louis de Broglie, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. There were disagreements among them. According to standard accounts, the 1927 Solvay Conference represents the pinnacle of the debate over the interpretation of quantum mechanics. But before we proceed, we need to remember that in classical mechanics, we deal with the macroscopic world, where matter and energy are distinct, meaning matter is not energy, and vice versa, energy is not matter. The idea of radiation being quantized started with Max Planck. That was in 1900. It was in 1900 when German physicist Max Planck published a paper that gave birth to quantum mechanics, or so the story goes. History reveals, however, that Planck did not immediately realize the consequences of his work and became a revolutionary against his will. Revolutionary because his idea became a contradiction to what was widely accepted at that time. Planck studied the intensity of light of various frequencies emitted from heated solids at different temperatures. During an experiment, a hot iron bar predicted to turn blue in color became red instead. Planck had to revise classical ideas of light being a continuous collection of electromagnetic waves to light consisting of bundles of energy or quantized. The figure in this slide shows an illustration of the concept of energy being continuous and that of energy being quantized. Planck concluded that energy can only be given off in bundles or packets of certain energies called quanta. The energy E of a single quantum of energy is given by the equation E is equal to h nu, where h is the Planck's constant and nu is the frequency of radiation. An equivalent equation makes use of C over lambda instead of nu, where c is the speed of light and lambda is the wavelength. According to his quantum theory, energy is always emitted in integral multiples of h nu. For example, 2h nu, 3h nu, or 4h nu, but never in between. Like, for example, 1.3 h nu or 2.43 h nu. For his discovery, Planck earned a Nobel Prize in 1919. Then came Albert Einstein, who used Planck's theory to solve another mystery in physics, the particle nature of light. 5 years after Planck presented his quantum theory, another German-born physicist, Albert Einstein, used the theory to solve another mystery in physics, the particle nature of light in the photoelectric effect. While well known for his theory on relativity, it was his work on photoelectric effect that earned him a Nobel Prize in Physics in 1921. Photoelectric effect is a phenomenon in which electrons are ejected from the surface of certain metals exposed to light of at least a certain minimum frequency called the threshold frequency. There is a required threshold frequency for it to happen. The photoelectric effect could not be explained by the wave theory of light. Einstein, however, made an extraordinary assumption. He suggested that a beam of light is really a stream of particles. These particles of light are called photons. Using Planck's quantum theory of radiation as a starting point, Einstein deduced that each photon must possess energy E given in the equation. E is equal to h nu. Einstein's theory of light posed a dilemma for scientists during that period. On one hand, it explains the photoelectric effect satisfactorily. On the other hand, the particle theory of light is not consistent with the known wave behavior of light. The only way to resolve the dilemma is to accept the idea that light possesses both particle-like and wave-like properties. Depending on the experiment, light behaves either as a wave or as a stream of particles. This concept was totally alien to the way physicists had thought about matter and radiation, and it took a long time for them to accept it. In 1913, not too long after Planck's and Einstein's discoveries, a theoretical explanation of the emission spectrum of hydrogen atom was presented by Danish physicist Niels Bohr. Reviewing the Rutherford's atomic model. According to this model, an atom is made up of mostly empty space. And there exist electrons with spaces revolving around the nucleus in their fixed paths. The nucleus is positively charged due to the presence of protons. And in addition to the protons, neutrons are also present in the nucleus. But there are drawbacks in the Rutherford's model. This model, known as the classical model, was very much accepted at that time. However, Almost as soon as Rutherford proposed his nuclear model, a major problem came up. According to the laws of classical physics, an electron moving in an orbit would experience an acceleration towards the nucleus by radiating away energy in the form of electromagnetic wave. Thus, such an electron would quickly spiral into the nucleus and annihilate itself with the proton. So it will quickly spiral into the nucleus and get annihilated with the protons. To explain why this does not happen, Bohr postulated that the electron is allowed to occupy only certain orbits of specific energies. In other words, the energies of the electrons are quantized. The electrons in an allowed orbit will not radiate energy and therefore will not spiral into the nucleus. In his model, electrons, electrons travel around the nucleus in circular orbits similar to those of the planets around the Sun. However, in contrast to the planetary orbits, which can theoretically exist at any distance from the Sun, Bohr's orbits can only exist at specific fixed distances from the nucleus. The energy of each Bohr orbit was also fixed or quantized. This is again using the concept of energy being quantized. Bohr called these orbits stationary states, and suggested that although they obey the laws of classical mechanics, they also possess a peculiar mechanically unexplainable stability. Bohr further proposed that, in contradiction to classical electromagnetic theory, no radiation was emitted by an electron orbiting the nucleus within stationary state. Okay, so like this one, if within stationary state, emit, it will not radiate or emit some radiation. But when the electron jumped or made a transition from one stationary state to another, that radiation is emitted or absorbed. So from inside to outside, it will absorb energy. If it's going from outside to inside, it will radiate energy. Bohr made use of the emission spectrum to prove his point. A little review on the concept of light. In the 17th century, Newton showed that sunlight is composed of various colors by passing it through a prism. The array of colors make up the spectrum of visible light. This is the continuous spectrum. Since then, chemists and physicists have studied the characteristics of emission spectra emitted by substances. This figure shows images of continuous spectrum and line spectrum or emission spectrum. Continuous spectrum is generated when the light source used is sunlight or white light. Line spectrum or emission spectrum is generated when the light source used comes from excited atoms of certain elements. The emitted light can be observed as a series of colored lines. These are the lines with dark spaces in between. These series of colored lines are called the line or atomic spectra. Each element produces a unique set of spectral lines. No two elements emit the same set of spectral lines. Therefore, elements can be identified by their line spectrum. Shown here is the experimental arrangement for studying the emission spectra of atoms and molecules. In this figure, the discharge tube contains hydrogen gas, the same as the one studied by Bohr. The discharge tube also contains two electrodes, positive and negative. As the electrons flow from the negative electrode to the positive, they collide with the gas. The collision process eventually leads to the emission of light by the atoms or molecules. The emitted light is separated into its components by a prism. Okay, so this is the prism. Each component is focused at a definitive position according to its wavelength to a detector. Okay, so according to its wavelength, bigger wavelength, smaller wavelength. The colored images are called spectral lines. Bohr attempted to develop a model for the atom that explained the atomic spectra. He reasoned that the emission spectrum of an atom consists of discrete lines because the stationary states exist only at specific, fixed energies. The energy of the photon created when an electron makes a transition from one stationary state to another is the energy difference between the two states. Transition between stationary states that are close, together will produce light of lower energy, meaning longer wavelength, like this one. So lower energy, longer wavelength. Then transition between stationary states that are farther apart, like this one. So bigger energy, smaller or shorter wavelength. For his study, Bohr earned a Nobel Prize in 1922. But in spite of the initial success in explaining the line spectrum of hydrogen, including the correct wavelength, the Bohr model left many unanswered questions. It did, however, serve as an intermediate model between classical view of the electron and a fully quantum mechanized view, and therefore has great historical and conceptual importance. Nevertheless, it was ultimately replaced by a more complete quantum mechanical theory that fully incorporated the wave nature of the electron. This is the end of part 1. A sequel to this is coming up. Please subscribe to my channel and thank you for watching.